Okay, in the topic subsystem design, we are going to study about our subsystem counter. As you have seen in IC designing at subsystem level, has to follow data path and hierarchy. And hierarchy goes to top-down design methodology and satisfying the three entities: less area, low power, and high speed. We have come across so many subsystems, combinational circuits and sequential circuits. In this class, we are to go for designing of your counters. So first we'll start with counters. We'll define a counter. So what is a counter? Counters are sequential circuits which count through a specific state sequence. So you can design to count through a specific state sequence, and that is with respect to a clock. So for each clock pulse, we can change the state of your flip-flops, and over a set of clock pulses, we can make it count through a specific state sequence. What is specific state sequence? You can make it to act as a up counter, down counter, or you can also count through other fixed sequences. So you can make it to act as a up counter for a certain duration, then down counter for a certain duration. So counters are sequential circuits which count through a specific state sequence. They can count up, count down, or count through other fixed sequences. So we are having two different types of counters. Ripple counters or asynchronous counters or synchronous counters. So in ripple counter, clock is connected to the flip-flop clock input on the LSB bit, and for all other flip-flops, flip-flop output of one will act as clock to the next one. So this is not synchronous, it is asynchronous. So output of one flip-flop will act as clock to the next stage. So output is delayed more for each bit. So, and for if you go for synchronous counters, the clock applied is same. So what do you mean by clock? Clock is nothing but a sequence of pulses, high and low, with duty cycle 50%. So what is 50%? The on time is equal to off time. So it is a set of sequence of square pulses where on time is equal to off time, which is having 50% duty cycle. So that clock, if it is applied to all the flip-flops simultaneously, then it is called synchronous. And you can design the logic to make it as to count as a specific state sequence. You can count from 0 to 1, 0, 1, 2, 3, 4, 5, 6, 7. That is up counter. 7, you can start with initial value as 7, 7, 6, 5, 4, 3, 2, 1, 0 down counter, or any state sequence. Okay, that state sequence is under your control. So next here, asynchronous counter or ripple counter. So in the right side diagram, we are showing one flip-flop where clock is the input and it is positive edge. So you can see the triangle symbol, that is a positive edge. And here we are designing a T flip-flop, and that is using a D flip-flop, where what is D flip-flop? Data flip-flop. T flip-flop means toggle flip-flop. For toggle flip-flop, for every clock pulse, output will be complement of the input. So how to generate complement? Output value must be given to a NOT gate, and that must be given to the input. But instead of giving to a NOT gate, for a flip-flop, you get two complementary outputs, Q and Q bar. So that Q bar is fed as input to the flip-flop. So if you see the first flip-flop where output is A, we are connecting that black color dot output A bar as input to D. So for every clock pulse, the complemented value will be given as the input, and this output is acting as clock to the next flip-flop whose output is shown as B. Okay, so if you see, the same output is fed as clock to the next stage. Okay, so if you see the point, the clock input for the flip-flop B is nothing but complemented output of flip-flop A. So output for A flip-flop is capital A, but we are connecting A bar as clock to the next stage, and all these flip-flops can be reset to the initial stage by the reset button. So once you click reset as 1, so this terminology is you can go for an active high or active low. So if you don't keep a bubble, it is active high. So active high to the reset will make it come to the initial stage. So first CP tells it is a clock. It is a set of on and off pulses. So this square pulses on and off with duty cycle 50%. On time is equal to off time. Together they form a clock. So it has a transition from 0 to 1 and 1 to 0. So whenever there is a 0 to 1 transition to the clock, your output D, okay, output D so look into the waveforms. Whenever CP bit was 0 to 1 transition, at that time clock transition was occurring. At that time input is fed to the output. Okay, input is fed to the output. What is the input? Already A was 0 initially, means A bar is 1. So that 1 is fed as input to the D bit. Okay, so once you apply a clock, the 1 is fed as output. So there is a transition from 0 to 1. If you see, there is a transition from 0 to 1. So this will remain as long as there is a next clock transition. So next clock transition is 0 to 1. So when there is again a clock transition 0 to 1, when again there is a clock transition from 0 to 1, the output will change from 1 to 0 because already A is 1, means A bar is 0. This 0 is fed as again input to the, this 0 is fed as again input to the first flip-flop. And whenever there is again clock transition, this 0 is fed to the output, because it is a normal D flip-flop implementing as T flip-flop. Okay, so output for every clock pulse, output will do toggle of the input values. So the toggling, how we are achieving by applying A bar as input to the D. So you can consider it as a D flip-flop only. The only thing is the input fed to it is a complementary value of the output. So like that, for every clock pulse, your complemented value is fed. So the 0 becomes 1, 1 becomes 0. So like that, you are going to get output A as 1010 transitions with slight delay. So the delay you can analyze with respect to CP. Now this A has its A bar. Okay. It has its A bar, which is reverse of this A, complemented value of this A, because that complemented value of A is acting as clock to the next flip-flop. Okay. So here also B is the normal form. B bar is fed as the input. So if you analyze as a D flip-flop, for every clock pulse, D input is fed to the output. And as a T flip-flop, we are complementing the, we are going to toggle the output. Okay, so for getting the toggle operation, we have given output complement value as the input. Okay, now if you see, here A is having 0 to 1 transition, then A bar is 1 to 0 transition. So that is not counted. If you see the arrow mark pointed where A is 1 to 0 transition, then A bar becomes 0 to 1 transition. So where A is 1 to 0 transition, there A bar will be 0 to 1. So for that 0 to 1 transition, your B value will change from 0 to 1. And again, where A is 1 to 0 transition, there A bar is 0 to 1 transition. At that time, again, B value will change from its present value. Present value is 1. So next value becomes 0. So like this, you are going to achieve ripple counter or asynchronous counter where clock is not synchronous to all the flip-flops. So you can make it to add base. This is the only 2-bit flip-flops. If you add 3 bits, it will count from 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, if you add one more bit, additional bit to D, it becomes, okay, it becomes a 4-bit asynchronous or ripple counter where you can get transition from all zeros to all ones. So for a 2-bit, it is changing transition as 0, 0, 0, 1, 1, 0, 1, 1. Again, it will reset to 0, 0, 0, 1. And in the diagram, you can see the blue color lines are telling the state transitions. So first CP 0 to 1 transition is changing A value, but for changing B value, you require complement of A. So A is 1, 0 means B is 0, 1. Sorry, A is 1, 0 transition means A bar is 0, 1 transition. So whenever A bar becomes 0 to 1 transition, second flip-flop B output will make transition from its present state. So here A is 1 to 0 means A bar is 0 to 1. At that time, B is changing. So these circuits are called ripple counters because each edge sensitive transition, positive in the example, causes a change in the next flip-flop state. And the changes ripple upwards through the chain of flip-flops. Each transition occurs after a clock to output delay from the stage before. So here we want to represent the delay produced in a ripple counter. So it is initialized. We have considered a 3-bit counter where 3 flip-flops initial values C equal to B equal to 1 is all are 1. In decimal value it is 7. And for next clock increments, the count value must become 0. Okay. So here it is an up counter 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. So the decimal value is 111. So for the next clock, it has to be reset to initially all zeros. So here we are going to see the state transitions occurring at the outputs of flip-flops ABC. So for every clock pulse, the clock to output delay TPHL causes an increasing delay from clock edge for each stage transition. And thus the count ripples from least to most significant bit. So here least significant bit is A, most significant bit is C. So there are 3 flip-flops, outputs are C, B, A. And because of this count to clock to output delay TPHL. It is propagating from least significant bit to most significant bit. This delay throughout the flip-flops produces an n bit delay. Okay, so for n bits, it is n into TPHL. So here we want to eliminate the effect of ripples. So we are using a common clock for each flip-flop, and we want to generate a combination circuit to generate the next state. So for an up counter, you can use an incrementer, which is generating the next state. So the right side diagram is representing the D flip-flops, 4 D flip-flops, D3, D2, D1, D0, and corresponding outputs Q3, Q2, Q1, Q0. And each time this inputs will vary. And because clock is common, it will count from 000 to 001 to 010, 011, 100, 101, 110, 111. So this increment values will be fed to the D. For every clock, D is returned to Q. So we have to design this incrementer such that the hardware logic is incrementing the values and giving it to the D inputs. So here the incrementer logic is analyzed with a XOR gate and AND gate combination, and this AND gate is nothing but carry output. So we have a enable pin. Once you enable it, initially output is 0000, and those are fed as an input, and your enable bit is 1. So 1 into 0 is 0. Okay. So but 1 into 0 XOR operation becomes 1. So initially Q3, Q2, Q1, Q0. Initially Q3, Q2, Q1 is 0 were all zeros. Now it becomes 0, 0, 0, 1. And for one more logic, it becomes 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, so on, all ones. So that was done with the help of this incrementer logic. So we have to design an incrementer logic such that the internal logic XOR bit complements each bit, and AND chain is causing complement of bit if all bits toward LSB from it are equal to 1. And we are also using a count enable, forcing all outputs of AND gate to become 0 to hold the state. And there is a carry out bit added as part of the incrementer, and this counter will enable to count, act as a 4-bit counter. So left side there is an incrementer logic. You can apply the values. Each value it is fed to an XOR gate, and that output is fed to D. Whenever there is a clock pulse transition, the inputs are written into the flip-flop, and it changes the value of Q. Okay. So what is flip-flop? It is a edge triggered flip-flop. So for every edge trigger, Q equal to D. So earlier we have seen one incremental logic for synchronous counter using a carry chain logic, where the symbolical representation is Q3, Q2, Q1, Q0 are the outputs. There is an enable pin and a clock at the input side, and there is a C out bit. And here the carry chain is analyzed with a series of AND gates through which the carry ripples, and this is yielding long path delays, and this method is called serial gating. We want to replace the AND carry chain with all AND gates in parallel. So if you see the previous diagram, this AND gate was producing the carry to ripple through all these gates. So this series of AND gates through which the carry ripples is yielding long path delays in this previous diagram. So this was replaced with an AND gate in parallel. So this method of designing the AND gates to generate Cout is called series gating. But whereas this method of designing each stage corresponding Q value and C1 is called parallel gating. It is like carry look ahead adder, and it reduces path delays. And this symbol is for synchronous counter. And what are the other counters you can analyze is down counter, where count is decremented from a initial value. So instead of upward, here you are going to count downward. So, and you can also go for an up down counter where count up or count down depending on value of the control input, such as up or down. And parallel load counter where it has a parallel load of values available depending on the control input. And you can go for a modulo counter. So modulo counter is like divide by n. So counter is designed such that it is counting up to a specific value. Count is the remainder of division by n, or it is a power of 2, and you can make it an arbitrary number of states. For a BCD counter, it will count up to 0 to 9. It is called modulo 10 or BCD counter. So here we are also showing one counter with a parallel load, where along with enable pin we have a load operation. So this load operation is going to make it as act as when load is 0, it is when count value is 0. Okay. So to the left side there are two bits, one is count and one is load. When count is 0, it will hold the stored value. So all Q3, Q2, Q1, Q0, it will hold the same value. But once count bit is 1, it is going to count as up counter. So 000 becomes 001, 001 becomes 010, like that. It becomes all ones for a 3-bit counter. For a 4-bit counter, it is all zeros to all ones. So that depends on the count bit. Count bit is 0, it holds the value. Count bit is 1, it is going to act as an up counter. Now, if load bit is 1, what is happening? You can load your data D values onto the D3, D2, D1, D0. So from that value, you can make it as act as an up counter. So that is created with this logic. So synchronous BCD counter. So BCD itself, it is telling it is can count up to modulo 10, that is 0 to 9. Okay, so the combinations from 1010 to all ones are not considered, they are don't cares. So you can see current state in 8421 format, it is Q8, Q4, Q2, Q1, which is all zeros, 001, 0010, so on 1001. So if it is acting as a synchronous counter, for every clock pulse, 000 becomes 0001. For the next clock pulse, 0001 becomes 0010. For the next clock pulse, 0010 becomes 0011. For the next clock pulse, 0011 becomes 0100. So it is counting 1 bit. So finally, for 81000, it is 1001. Then for the next clock pulse, 1001 becomes reset to its initial value. Okay. So how you have to analyze is, for each next state values, you have to see when the output is 1. So you have to generate SOPs based upon the K map. So you have to take those combinations for which output is 1. You can map on a K map. You can use the don't cares, then go for 2-cell, 4-cell, 8-cell groupings, then generate the equations like this, which are optimized, 2-level optimized next state equations for D1, D2, D4, D8. So based upon that, you can create the hardware related to this one. For D1, D1 input, this is the hardware. For D2 input, it is this one. So this combination of output values are taken and given to corresponding AND and OR gates, and that is fed as input to the D values. So here, if we are not considering don't cares, what happens is for a 4-bit, the next states are written as 1010, next state is 1011, and 1011 next state is 0110. So like that, all the next states are written and they are represented in a state diagram. For the BCD counter design, if an invalid state is entered, return to the valid state with 2 clock pulses. For an n-bit binary counter, whether it is synchronous or asynchronous, you can use a clear pin and load pin. Okay, so everywhere you have to write the current state and present state based upon the modulo values. It is an asynchronous 4-bit binary counter with an asynchronous clear pin. So this clear pin, what it does is asynchronous clear pin to make it as act as a modulo 7. So once it is modulo 7, means it is up to counting from 0 to 6. This clear pin will make it to this clear pin will make it to come to initial state. So it counts from 0, 1, 2, 3, 4, 5, 6. Once it is all sevens, it is 7. It is all, it is 7 means Q2, Q1, Q0 are all ones. Those ones are given to an NAND gate. NAND gate output is 0 and this 0 is fed as input to the clear pin. Clear pin is a active low signal. So that 0 becomes 1. And once it is 1, all the outputs Q2, Q1, Q0 becomes initialized to 0. So this type of modulo 7 counter will detect counting from 0 to 6, 0 to 7. Okay, once 7th bit once comes, it becomes again 0. So 0 to 6 only it will count. Once 7th bit comes, it will detect it as 0, 0, 0. So the same logic is applied for a synchronous load. Here we are using a synchronous load count of 6. So a synchronous 4-bit binary counter with synchronous load pin and asynchronous clear pin is used to make it as a modulo 7 counter. So the load feature to detect count 6 and load in 0. Here the count value is counting from 0 to 6. Then again it is 0. So using don't cares for states above 6, detection of 6 can be done with load Q4 and Q2. So here what we have done is in D3, D2, D1, D0, we have written all the inputs of this 4 D flip-flops as 0, 0, 0, 0. The moment it counts from 0 to 6. Okay, once it counts 6, 6 means Q2, Q1, Q0 is 1, 1, 0. So that 1, 1 is given to an AND gate. That AND gate output is given to a load. So once it is a load pin, just Q3 becomes D3, Q2 becomes D2, Q1 becomes D1, Q0 becomes D0. So all are initialized to zeros. Okay, so that's why it is a synchronous load and asynchronous clear pin. So what is asynchronous? So this reset, if you apply to active low signal, that is going to clear. But here our count value is controlled by load pin. So similarly, you can go on adding preset pin, clear pin, load pin to your design. So here what we are doing is we want to use a load pin, which is a actually we are designing it as a modulo 6 counter. So we are good. We are doing the load operation. So D3, D2, D1, D0 are fed with 1001. Synchronously preset 9 on reset and load 9 on terminal count 14. Okay. So it is 1001 means 9. We want to load that data, and for which we are using modulo 6. So we are using modulo 6 as the design. So once it is 6, 0, 1, 1, 0, you are going to generate an output 0, which is fed to your OR gate, and that is acting as a load. So asynchronous 4-bit binary counter with a synchronous load. Asynchronous 4-bit binary counter, asynchronous 4-bit binary counter with a synchronous load pin. So in the exam, you don't need to add all this reset clear pin. You can just go on designing an asynchronous counter as a ripple counter like this, 2-bit, 3-bit or 4-bit, or you can go for designing a synchronous counter based upon your state table, where taking the current state and the next state, you can generate corresponding input bits, and those input bit values, when they become 1, that combinations you can generate a K-map, and you can generate the hardware like this. So the hardware for D1 is directly Q1. For D2, it is a combination of Q2 plus Q1, Q0. So there is an AND gate plus OR gate given inputs as outputs of the flip-flops. So next state is generating the present state. Okay. So like that, it will count from all zeros to all ones if you act as a mods. Uh, uh, it is a 4-bit counter. It is a mod 16 counter, 0 to 15 it will count. If you make it as a mod 10 counter, it will count from 0 to 9. So next we'll discuss some more topics related to counters. So already you have seen counter is a sequential circuit which counts number of clock pulses. So the topics to be dealt are, already we have seen synchronous and asynchronous counter. So its characteristics, ripple up counter, ripple down counter, and how it acts as a frequency division circuit. So count by definition, one input clock, outputs following a definite sequence, count up or down counter, increment counter, decrement counter, controlling the sequence of events or states, are acting as a divide frequency, or it can be used for memories. So here, coming to counters, first you have to decide the number of bits. This number of bits will decide the number of flip-flops to be used, and will also decide the count value. So if you select number of bits as 4, it will count from 00000 to all ones in binary form. If you take it as a count bit as 8, it will count from up to 2 power of 8. So modulus of count number of states. Modulus of counter number of states. So you can go for a decade counter counting from 0 to 9, or you can go for a 4-bit counter counting from 00000 to all ones. So analyze up counters, down counters. Both can be synchronous and asynchronous. So this is the ripple counter. This 4-bit counter has 16 states because there are 4 flip-flops. Here we are using a JK flip-flop, and this JK flip-flop, all inputs are connected to 1 and all clear and preset pins are connected to 1. What it means is, in this diagram, so you can see we have made preset and clear pin inactive by giving it to a 1. As bubbles are connected, then this 1 becomes 0. So they are inactive, and all JK flip-flops are in the toggle mode. So how you make it act as a toggle mode? When both the inputs are 1, your output is complement of its present value. Q becomes Q bar. When both inputs are 1 for a JK flip-flop, Q becomes Q bar. And here, this 4-bit counter has 16 states, counting from all zeros through all ones. Then again, it will go to reset to 0. So it is called a modulo 16 counter. So whenever there is a, if you see the clock applied, will be having a bubble in this your diagram. For each flip flop, if you see to the clock input, we have kept a bubble. Bubble indicates it is a negative edge trigger. Okay, whenever there is a transition from 1 to 0, this first flip flop will generate the will change the value Q from 0 to 1, and this will act as clock to the next flip flop. So there is a 1 to 0 transition in the clock. Your transitions of all the 4 flip-flop outputs will vary, and this ripple counter is going to count from all zeros to all ones. So here if you see, flip-flops triggered on high to low pulses. So clock toggles. Oh, okay. So if you see, so in the same diagram, both JK inputs are 1. Both JK inputs are 1. Q becomes Q bar. And so for a clock input, whenever there is a high to low transition, your first so each output of flip-flop, you can see whenever there is a high to low transition, the output is varying from 0 to 1. And whenever this is from high to low, output is varying from 0 to 1, each flip-flop output. Whenever the third row is going from high to low, again there is a transition from 0 to 1. So if you study in the reverse order, it is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Like that, finally it is all ones. So you have to read the Q3, Q2, Q1, Q0 in a reverse order. So this is a ripple counter. and we want to make it as a decade counter. So for that, we are connecting the logic is we have connected two outputs like we have shown in the earlier part. Decade means it is 0. It is a 4-bit counter. No, it will count up to 1001. So 1001. So 1001. Both the ones must be given to AND gate, and that output is fed connected to the clear pin, where it will make our flip-flop outputs to come to initial state. So this is active low pin. Here also output generated is 0. So 0 acting applied to all the clear pins. So the 0 makes it 1. So for that 1, output becomes all zeros. So count is at 1001. For the next clock pulse, okay. So you are going to make the counter reset to all zeros. So this is regarding decade counter. And this is a down counter where the flip-flop is, all flip-flops are initialized to 1111. And for every clock, they will do down counting, changing the ripple counting from all ones to all zeros. So here, this is Q, Q2, Q1, Q0. And again, it is an asynchronous counter. So how that is done is, output of first flip-flop is fed as clock to the next one. So based upon this transitions, we are going to see a down counter. So this you have to, for a up counter, normal output of each flip-flop is acting as clock to the next counter. Complement form of your output will act as a clock to the next state. So here counter used for frequency division. So in each state, this ripple counter was designed with a 4-bit flip-flop, where output, if you see in this diagram, it is an up counter. Okay. So if you see output Q is acting as clock to the next stage. And this is bubble means it is a negative edge triggered. Without bubble, both JK inputs are 1 means whenever clock pulse comes high to low, your output changes to toggles its previous value. If 0 is there, it becomes 1. 1 is there, it becomes 0. And if you see the uh, clock pulse applied is initially clock pulse applied is 800 hertz, but as clock is propagating from one stage to another stage, so the final LSB flip-flop clock pulse is, because you know from you have seen each of the negative edge is generating. So here if you see, each of the negative transitions high to low was generating one more clock pulse whose time period was uh, this is a high frequency, then the frequency is reduced, so time period is increasing, the on time off time period is increasing, the next 2s output time period is more, next 2s 4s output is again more. So as time period is increasing, corresponding frequency is reducing. So first flip-flop output is reduced by 4 by 2, it is 400 hertz. So the clock applied to the first flip-flop is having frequency 800 hertz. Okay, F is equal to 1 by T. So the time period of both T on plus T off is nothing but 1 by 800 hertz. So now the output generated of first flip-flop is nothing but clock to the next stage. So that is reduced by 2 times, it is 400 hertz. And in the next case, next flip-flop output is divided by 4, it is 200 hertz. And the third flip-flop output is divided by 8, it is 100 hertz. And the fourth flip-flop output is divided by 16, it is 50 hertz. So like this, uh, we have designed in synchronous and asynchronous counters where we can see that the it counts the number of clock pulses with respect to clock applied, whether it is asynchronous or synchronous. So once again, we'll go through the comparison of both the counters. So as we discussed, for ripple or asynchronous counters, flip-flop of one output, QA is fed as clock to the next stage. If there is a bubble, it is a negative edge triggered. Without bubble, it is a positive edge triggered. And if clock is same for all the flip-flops, it is synchronous counter. So as discussed earlier, asynchronous ripple counters, clock is not same. They're not clocked simultaneously. Circuit is simple. Speed is slow as clock is propagated through number of stages. Whereas for synchronous, there is no connection between output of first to the clock of next flip-flop. Flip-flops are clocked simultaneously. Circuit becomes complicated and speed is high. And the synchronous counters can be analyzed in terms of three ways: up counter, down counter, up down counter. Counters anyway, not only synchronous, asynchronous, synchronous, both we can make it to design as three methods. This was regarding the subsystem design counters. So you have to take 3-bit or 4-bit. Based upon that, make a state transition, current state to next state, then write down the corresponding inputs based upon the flip-flop selected, D flip-flop or so which transition of Q to Qn Q bar, Qn plus 1 will give the Q to Qn plus 1 will give corresponding inputs. Write down those inputs and for which input values it is 1, those minterms you do an K mapping and generate the hardware to be connected to the input pins, inputs of the flip-flops. So this covers the topic counters.